guys have the data sheets of the Cortex M3 processor? Please open the data sheets. So, okay, on the first page itself there is features and benefits of the processor. So there you will find what are the features of this ARM controller that we are going to use. Okay, in the ARM 7 TDMI, what does TDMI stand for? T stands for D? Debugger. Okay. M? Sorry? Why other controllers can't do multiplication? Hardware multiplier. So M stands for hardware multiplier. And I? What is embedded ICE? In-circuit emulation. Okay. So here you can see in the features you find that in-system programming and in-application programming. That is another way of putting it, where the program can be loaded directly onto the system by using a compiler connected to the PC. That is in-system programming. You don't have to take out the processor from the board to do that, right? So let me just briefly tell you about the features. So it's an ARM Cortex M3 processor running at frequency of 72 up to 72 megahertz, right? This processor does not need an external crystal. It has an internal oscillator and can run up to 72 megahertz speed. Next, there is something very important called a nested vector interrupt controller. Have you used it? Have you used it in ARM 7 TDMI? Vectored interrupt controller? You have used it, right? In 8051, when you used to do programming, there were different interrupts, reset interrupt, then there were Gpio interrupt, timers, etc. All interrupts were there. All those interrupts were given priorities, correct? Reset was given the highest priority, okay, and the priorities go on changing. Now in an 8051, those priorities are fixed. You can't change those. But with the VIC, that is a vectored interrupt controller, you can actually assign priorities, different priorities to interrupts that you want. So based on whatever application you are building, you can actually assign priorities. Like a Gpio can be assigned a higher priority than a timer. You can do this with a vectored interrupt controller. Okay, that is how it is used. Then other than this, I think most of them are quite self-explanatory. You guys have used an ADC also? ADC also you have used, right? Okay. Board Dinayak? Any doubts? Any doubts you have in those features? No doubts? Yeah. See, when a program runs, when a code is running on a microcontroller, sometimes there might be errors where it is not able to fetch an instruction or decode an instruction, something like that. So basically your program gets stuck, correct? Now how do you recover from that? In a software, what do you use? If you want to see if a program is not being stuck, if it has to run continuously, what do you use? Software interrupts directly. Exception handling. Don't you basic some kind of flags or something? That's the basic one. Okay. Now this is something like that, but built into the hardware. Watchdog timer, what it does is whenever the microcontroller is reset from the start, the timer starts counting up, and you can set the interval there. Like usually it is set at 10 millisecond. So at every 10 millisecond, the application programmer, whoever writes the software, they have to reload the watchdog timer within that particular interrupt, within that particular interval. So that means the application is continuously running. If by chance the application, whatever you write, fails to update the watchdog timer, the system resets automatically. It starts from the beginning. That's why it is called watchdog timer. Come to the page 6 of that data sheet. Pinning information. So see, this is the microcontroller that you are going to program. Okay, this is the microcontroller. Now in this particular page of the data sheet, in pinning information, you will have different kind of packages that are available for the microcontroller. You have any idea about the packages that are there? SIP, DIP. Other than this, what do you call this kind of a package? This one. This is a QFP package. It's quad flat package with pins. Quad flat with pins. That's a QFP package. Those of you have the boards, you can see the pins are outside the microcontroller, correct? Right? So, and it's all on all the four sides, equal number of pins. That is the quad flat package with pins. If you scroll down, yeah. So this is one more another kind of package. This is QFN. Again quad flat, but no leads. The pins are not given outside. In this board, you can see this particular microcontroller, which is quite bigger in size, near the USB port. So this is a QFN package. You can't see the pins outside; they are below the microcontroller, there itself. Okay. So right, this is about the data sheet. So when you do the programming for any microcontroller, have you gone through a user manual for that? Yeah. Some of you don't know there is a user manual for microcontroller. Every microcontroller series comes with a user manual. This data sheet is hardly, I think, around 10 pages, something like that. Yeah, no, it's 74 pages. There is a user manual with 300 pages. So in user manual, you will find you will find the detail about each and every resistor that is there, which has to be used to program. In ARM 7 TDMI, did you do the resistor programming? Loading value into each and every resistor, right? So the same kind of programming you can do with this by going through the user manual. Okay, we will be using this a lot to do the programming. Now before this, let us first come to the GPIOs, which we will be basically using. There are 42 GPIOs on this which can be used, and all of them are multiplexed. You know what multiplexing is, right? So the GPIOs, the pins that are there, they can be used for other peripherals also, with the other peripherals, like some of them are multiplexed with a serial block, which can be used as a UART or an I2C, something like that. So this is how GPIOs can be used. So for configuration of GPIOs, there is you know the basic GPIO functioning, just on and off. This works at a voltage of 3.3 volts, right? In GPIOs, have you heard about the resistor pull up and pull down? In GPIOs, there are pull up and pull down resistors, correct? No idea. Okay. You haven't come across pull up and pull down resistors at all? Only some. Okay, in general you know about pull up and pull down resistors. So what do they do? Okay, so you know that basics, right? So assume this is a digital block. Okay, this is output. So there are two inputs, A, B. and here is a switch. You are able to see this, okay? So this is a digital circuit. So these are inputs A and B, and there is an output. Now when I close these switches, if I close both of these switches, A is 0, B 0, correct? And based on the digital logic, we'll get the output here, right? What if I close only A? I make A 0, but I don't close the B. What happens now? The logic may work or may not work. Why? Because the voltage value on B is not fixed, right? Now in this case, to solve such scenarios where a particular input is not connected to any voltage, either 0 or a high, we connect pull up or pull down resistors. Pull up is nothing but you just take this, take a resistor, connect it to 5 volt. Similarly here, this is a pull up system. So what will happen in this case? In this case, even if I don't connect B anywhere, it is by default taken as 1. In case of a pull down system, by default it will be taking it as 0. Now in microcontrollers, the GPIOs, each and every GPIO has a pull up and pull down resistor system. When a GPIO is configured as an input, to prevent any unintended triggering of the logic from the voltage levels on that particular pin, these pull up and pull down resistors are used. So even for that, there are simple resistors in which you can load the values, and the microcontroller itself will enable or disable the pull up and pull down resistors. When you use it as an input, this is very useful. So if you you know about the logic levels on a microcontroller, right? How logic 1 is determined on a 3.3 volt system. Logic 1 is 3.3 volt, logic 0 is 0 volt, but these are not absolute values. There is a range in which it is determined. Usually it is 3.3 to 2.7 volts. So any voltage between 2.7 to 3 is determined as a logic 1, and 0 to 0.7, 0.8, something like that. So this voltage is calculated as logic 0. So now you can understand, if there is no pull up or pull down available, and if by chance the logic level falls down at this or goes above this, this can happen. Why? Is there any case why this can happen? Sorry? How practically, how do you introduce noise in the system? But the most common way this triggering happens is due to static. When you touch the input output pins on a board, right? All of you, when you are wearing shoes and you touch the input output pin, your body's static electricity is just enough to raise the inputs to this level. For a small interval, not a long interval, for a small interval, it is able to raise the input voltage level to this. So to prevent this kind of triggering, we use the pull up and pull down resistors in a GPIO. Okay. Before going into coding, there is one important thing I forgot to discuss. It's about the clocking systems in a microcontroller. In a basic microcontroller like 8051, you use what crystal? What did you use for most of the programming purposes? What was the clock? 12. Huh? Was it not 11.0592? You rounded it up to 12. 11.05 to 12. Why 11.0592? Any idea? Sorry? Yeah, that's a complicated thing, but the basic thing is on UART there are particular baud rates, correct? 9600, 4800, something like this. To achieve that particular baud rate, the clock frequency has to be divided, right? So for that particular reasons, that exact value 11.0592 that is used to get that particular. So it's not 12, so it's 11.0592. Now in a system like this, in an advanced microcontroller like this, you don't connect an external oscillator, external crystal. So internally there is an oscillator present which can give you different kind of frequencies. Usually one of them is a main clock which will power the each and every peripheral core of the system. That clock in this particular microcontroller is set as 12 megahertz. Okay, it is set as 12 megahertz. Now in addition to this, there are other clocks available on the system. For example, this system doesn't have an ACLK. There is something called an ACLK in some systems. This system has a PCLK for a peripheral clock. So all the peripherals that are on board, right, like GPIO, UART, serial interfaces, all of them, these can be run at a different frequency than the main core. So even if your main core is running at a 12 megahertz, your peripheral clock could run at 48 megahertz. You could program to do it that. So each and every, so this whole circuitry is included inside the microcontroller itself, and this is what you configure in your program. Whenever you write a program, I don't think you have done this in your labs, or you have not done this, but it will have been done as a startup code in whatever interfacing programs you do, right? There will be a startup code which will run in the beginning. That is what disables the watchdog timer also. You never used watchdog timer in the labs, right? But the startup codes usually disable the watchdog timer in the beginning because we don't need it for testing purposes, etc. Only when it goes to the application level, when it is being launched, at that time we use the watchdog timer. So the startup code disables watchdog timer, configures the clock of the system, whatever has to be used. So that is done by the initial startup code which is there. Now in clock, initially it is only 12 megahertz for this system, but using a PLL, this is able to generate a clock of up to 320 megahertz. You have studied the concept of PLLs, phase lock loops. That is not for this workshop, so it's a quite complex system where it is able to generate different clocks from a single source. From a smaller source, it is able to generate a large clock. So even with a small source like 12 megahertz, we can generate clocks up to 320 megahertz in this particular case. For example, in USB, for USB specifications, whatever USB devices are there, a particular frequency of 48 megahertz is required for internal working of this. Now when such different peripherals require different clocks, it doesn't make sense to add different crystals for each of them. That is why all the clocks inside are connected to the system, the main clock, which can be configured using resistors to generate any clock that you want. We'll come across that in the startup code when we'll be doing that. So that is the main system clock, right?
Like